Okay, good morning, good afternoon, good evening, everybody that called in today for our May PCT monthly meeting. So Meredith recommended we go through real quick and do a roll call.
Actually, does the inventory.
There seems to be some background noise. I think just make sure you're on mute if you're not speaking. Thank you.
Yeah, or we could talk about inventorying too. That's interesting stuff. But yeah, let's go through real quick, and I'll start off here with the roll call. I'm Benjamin Jones, currently with USGS, one of 3 PCT team leads, along with Andrew Balzer and Christina Schottel. Andrew was not able to join in today, but I believe Christina's here, so maybe Christina, you can go next and introduce yourself.
Yeah, hi, this is Christina Schottel. I'm at Northern Arizona University, and I am excited to learn today more about the craters, since that's a question I often receive if I talk to someone who doesn't know much about permafrost, and I always struggle a little bit with an answer. So hopefully after today, I will have a great answer.
Okay, and Marina, do you want to go ahead and introduce yourself since you're our speaker today?
I switched myself off, so I had to find the button. Can you hear me now?
Yep.
I think I'm introduced in written already. The announcement. I live in Moscow, and I'm sitting now in Moscow, but I work mainly in Siberia to study permafrost.
Olha, eu vou estar no Skype call.
Okay.
I'm not used to such format, so maybe I don't understand what is
Nope,
going.
that was perfect. Thank you. So I think we're going to have everyone who's in Alaska right now go ahead and introduce yourself. So if you're located in Alaska, speak up and let me know you're here.
Jeff Curry with the Department of Transportation Northern Region is here in Fairbanks.
Thank you. Welcome.
Ed Yarmak with Arctic Foundations is here.
Reginald Musket, UAF, Geophysical Institute.
Okay. Anyone else in Alaska? If not, then we'll move on to the West Coast.
Charlie Coven, Lawrence Breaker Lab.
Welcome.
And this is Clayton Elder. I'm not sure if you can hear me. I'm at JPL.
Mark Waldrop from USGS is on the phone.
Okay. Do we have anyone in Mountain Time?
Here's Elchin Jafarov, Los Alamos National Lab.
Moses Chirpanov, the Alaska Native Tribal Health Consortium.
Okay. Central Time? And East Coast?
This is Peter Griffith with the Arctic Boreal Vulnerability Experiment, NASA Goddard Space Flight Center.
Carolyn Russell, USGS, head of the Gas Hydrates Project based in Woods Hole, Massachusetts.
This, Sue Natali and others at the Woods Hole Research Center.
Hi, Sue.
Naomi Short, Canada Centre for Remote Sensing, Ottawa.
Ashley Rudy, Wilfrid Laurier University in Ontario, Canada.
And Frank Rack, NSF Office of Polar Programs.
Great. Anyone else from anywhere around the world?
There's a number of people who've put something into the chat window.
Thank you.
Yeah, I was just going to bring that up. Yeah, so a few folks don't have mics. So yeah, Santosh is on the call. Ronnie Dannon, Yuri Bornikov, Matt Heavner from Los Alamos, Rebecca Fry from BYU, and Rob Fraser and Yu Zhang from the Canada Centre for Remote Sensing in Ottawa.
Hi, here Gonçalo Vieira from the University of Lisbon in Portugal.
Okay.
Okay, wonderful. Thanks for coordinating that, Meredith. And hi, everybody. Thanks for introducing yourselves and for making our call this week. So as we mentioned, Marina Leibman, Dr. Marina Leibman will be giving our monthly webinar. But before we get to her presentation on the Yamal Craters, we tend to open up about 10 minutes of time at the beginning of these calls for people in the community to give some updates about recent research findings, ideas for collaborations, upcoming future scientific meetings or workshops, and or any other general announcements people would like to share about permafrost or anything relevant to IARPIC. So I guess I'll start off by opening it up and asking anybody if they'd like to make any announcements right
now. This is Peter Griffith with Above. Most of you probably got emails about the solicitation for phase 2 of Above, but that is, if you didn't, that has come out, and there's notices on above.nasa.gov about that. Also directly related to permafrost, we will be returning and to fly a subset of our permafrost sites with the L-band SAR in August of this year, and there's more information on that on the Above website.
Yeah, great. Thanks, Peter. Anybody have any questions related to the recent RFP from NASA Above? I can, I'll make a quick announcement about an upcoming symposium that'll be in Potsdam, Germany in September. It's September 10th to 14th. It's the 15th International Circumpolar Remote Sensing Symposium. So kind of a mouthful, but in short, the 15th ICRSS. Abstracts are due, I believe May 15th is the deadline for abstract submissions, but I imagine that will extend a month, probably extend the deadline out a month to about the middle of June. And so you can find information on, skip a couple slides here. You can find information on the symposium on, it's actually USGS website, alaska.usgs.gov /science/geography/CRSS 2018. So all the details are in there, and we're hoping to have a good turnout. We have about 4 invited speakers lined up already, and I believe our abstract submissions so far are about 28 or 30 right now. Anyway, hopefully people will consider coming and attending the 15th ICRSS. Okay, anything else of worthy of note currently before we get into Marina's presentation on the Yamal craters?
And if you don't have a microphone, you can always type it into the chat and I will record that as well.
Okay, no chats, Meredith? No, okay, awesome. Okay, well, I'll go back a couple slides here. Yeah, so I think we're fairly lucky that we were able to get Dr. Marina Leibman on the call to give this month's presentation. It's quite late right now in Moscow, I believe probably somewhere past 8 p.m. So thank you, Marina, for being willing to give a presentation late in the day there. She's going to talk about the Yamal craters. Her title is Yamal Craters, Permafrost, Climate, Methane Controls, and Triggers. So she's going to present on the craters based on 4 years of field monitoring, remote sensing data analysis, lab tests of samples taken from the crater walls, and the lakes that tend to form in the bottom of the craters, as well as the surrounding environments. She'll describe when the craters formed, what they observed inside, and how they developed following formation, and various approaches to potentially predict where similar features might form in the future. Okay, so at this point, I'll stop sharing my screen, Meredith, and then can you coordinate getting it over to Marina?
Yep. Marina, just let me know.
Okay, while that's going, oh, sorry.
No worries.
Yeah, I was just going to introduce Marina's a little bit in more detail while you guys are taking care of the screen sharing. So Marina graduated from Lomonosov Moscow State University in the Permafrost department. She has 2 postgraduate degrees. Her first is a candidate of science, which is more or less equivalent to a PhD, and the second one is a doctor of science. They're both in permafrost. Over the last 22 years, she's worked in the Earth Cryosphere Institute of Russian Academy of Sciences, the Siberian branch, and she's participated in a number of expeditions in various permafrost areas in the tundra and taiga regions, including Arctic islands of Svalbard, Franz Josef Land, and Novaya Zemlya, which I'm not sure if I can say that properly, studying various permafrost properties, ground ice types, and cryogenic processes. Now most of her research time is spent, her and her research team's research time is spent on studying the gas emission craters on the Yamal. Okay.
Then I may start.
Yep, whenever you're ready, Marina, go for it.
Yes, I'm ready, especially because you already summarized all I was going to say. So my mission now is just showing pictures, because for sure your real English is better than mine. So once again, I little bit changed the title since I sent you, and because of course I will speak a little bit about triggers and so on, but there's more about where, when, and why these craters form at all. Most we know these things from all of us, including myself, from the internet, where the information first appeared. And then these journalists' interviews, they somehow overloaded all our scientific work. And people are mainly trying to discuss with what is said in the internet and what we managed to study. So this will be more or less real science that we managed to do. Of course, it was a big team of people who are working with me. So my name is only the name of presenter, not of those who obtained all this data. So what do we know after 4 years of study since 2014? When and where did gas emission craters appear? We call them, we abbreviate them as GEC. What was observed inside the crater, how craters developed through all these years, and some landforms related to their formation. You may find again in the internet, and again I can say that we have to discuss with the internet, not with science. You may find information of 8, 9 thousands of craters that are and were ever. So this is not absolute true, but anyway, I will speak only about craters that I have seen myself, or from which I have undoubtless photo evidence. So those, I don't know whether you have the same colors as myself. There are 4 craters of light brown, 1 yellow, and 1 red. So what does it mean? These brown craters are those we visited on land. We did photos, GPS survey, and some of them sampling a lot. The yellow one is the last one in 2017. We were not there, but we got all the possible photo, video, and drone information on this crater to analyze things. And the red one is something very phantom. We have photographs which are different from other craters, which means that this crater really exists. But in the coordinates that were provided by this, the observer did not show any crater or satellite images. So it is somewhere there, and it was formed sometime then. So this is the table of doubtless craters with such strange names. Some of them were on Yamal, 2 were on Gedan Peninsula. Gedan is this one, with craters east of Yamal. By the way, this is Yamal. They formed the first one, though it is called GEC number 2, it formed in October 2012, was the earliest. Then several in 2013, and one last, I told you already, in June 17. Everyone asks immediately whether there is any connection of these craters with global climate change. I'm not using this term global climate change in my work because global processes are not something that can be easily related to what we observe. More important is local climate and change. Of course, change is important, but even more important is our climate fluctuations that happen year to year. 1 year cold, 1 year warm, 1 year even warmer. And for permafrost, it is most important. These fluctuations are most important to form specific processes. From this diagram, you can see this blue line is summer temperature, actual degree days of positive temperatures. And the brown line is mean annual air temperature. So this degree days of summer temperature, you can see that 2012 was an extreme summer after several years of more or less evenly distributed temperatures. And this, we think that we can rely on this information as one of the triggers for crater formation in 2012, 2013. Then we followed a couple, actually 3 rather cool years. And with these cool years, we did not have any other crater events. So one could have decided that it already stopped. But when comes hot summer of 2016, we started to expect the next event, and it happened, luckily happened in 2017. Only one crater, but it formed in the river channel, which by itself was something very strange. Some just this side information about the craters, which may be interesting. This crater number 1, it is 20 kilometers from the railroad subscribed of Anyankova. This railroad is a meridian taking people from the biggest city of the region north to the gas field. And this crater is only 4 kilometers by 3.8 kilometers from a gas pipeline, which takes gas from Yamal to Europe, by the way. And there is no population, but there are local nomad groups, reindeer herders, about 2,000 of them, nomadize in the vicinity of this crater, going north in spring and returning south in the fall. This is another crater to compare. This on Gedam Peninsula. It is very different from the first one, so I will sometimes compare them. It was more or less, it was observed by the local people very soon after it formed, so we can see this section on this photograph. It is more than 106 kilometers from the nearest settlement called Antipyuta. That's why this crater is called Antipyuta GC. And less, only 1,000 or little more people nomadize in the vicinity of this crater. Gedam is much less developed compared to Yamal, but it's the future of this area. In summer 2014, GEC1, and actually in summer 2016, we visited AntGEC, but the pictures show them on the same time, soon after they formed. You can see the GEC1 has a parapet, we call it parapet of the ground, which was thrown out of the crater and accumulated, loaded the sides of this, of the hull. And it is at the lower part, actually at the foot of the gentle slope, and all vegetated with willow shrubs. If you go down to the AntGEC, you can see it is a white parapet, is just sand. It does not form a good landform, but we can see it was sand. And the first thing to say, it is situated on the top and upper part of slope of this sandy terrace. So this one at the foot of slope and this one at the top. At first, we hoped to understand the terrain indications of the possible craters. After this two were studied, we understand that there is actually no terrain limitations to crater formation. After the last one formed in the river channel, we even less have any chances to understand what is the landscape, the surroundings, any properties seen on the images that can tell us that this place is specifically risky for crater formation. But all the craters, including these two, have one feature. One absolutely common feature is ground ice. We call it tabular ground ice, which is rather thick and vast layers of almost pure ice in the geological section. So this is ice, and this is ice also. This ice is covered by mainly clay, loam, silt, such deposits. And this ice is covered by sand, also the difference between these two craters. So surface deposits are also not indicating us possible crater formation. This crater number 1 shows the surroundings. You see with round lakes and other small lakes and more or less a big lake. What is interesting here is there are lots of slow processes not related to the crater. They existed before. These thermocirques, we call such landforms which are resulting from retrogressive thaw slumps, otherwise thawing this tabular ground ice and moving all these liquefied masses into the lake. And this is a landslide, which can be called actively detachment slide. It is not due to thawing of ice, but due to instability of the most surface deposits of the active layer. When we first approached this crater, it was, I would say, it was clear from the beginning, before we even know what it was, only that there was a crater, that it should be somehow connected with the gas. Simply because there is no other force that can make such an eruption because of permafrost. So the first thing we took with us was a gas analyzer. We had a row. It was impossible to go in the crater, and of course it was a little bit, I would say, I was afraid myself and was not positive to send somebody else to have a risk of entering this crater. But with the rope, we put lowered first video camera, and on the right you can see this freeze frame from this camera, this icy deposits, and at the very bottom, the piece of small lake. So imagine we look from the top down in this camera. The second lowering of the camera was with the gas analyzer, while methane concentration near the mouth of the crater was less than 3%, which is also very high. But at the bottom it was more than 9%, which is extremely high, and can produce a blow-up. We reconstructed this crater from satellite images and digital elevation model, and found it was, initially it was even in the wider funnel part, only 18 meters wide. Again, all these internet stories about enormous crater, it was not enormous. It was just a rather small but deep, which is something to talk about. The upper part of the section at the initial stages of this first crater showed stratified deposits of lots of ice, more than 50% of ice. But when it was somehow washed out, prosected from the surface, we saw that the stratification is vertical, not horizontal as we would expect. And as we saw later, after this deformed by crater deposits were destroyed by retreating walls. So vertical is deformed. Then slowly this little bit vertical structure preserved here. And you can see even traces traces probably of the core of the mount of which they created on. And then already in the fall 2015, which is 2 years after formation, the walls retreated so that we start to see normal horizontal stratification. This normal stratification we can also see in the nearest exposure slide. This is the lower right frame is photograph of the exposure in the thermocirque. And the guy center line.
We're getting some background noise. If everyone can make sure they're muted. Thank you.
So what did we do in these 4 years of study, which resulted in something? Is we did remote sensing data analysis, we did field surveys and monitoring, we did laboratory tests of samples taken from the crater walls, crater lakes, and surrounding environments. And we did dendrochronology of the shrubs from the crater and background tundra. Maybe I say a few words. I did not make this slide, but maybe interesting. Why dendrochronology? Because it shows all the impacts that may have that are documented in the size of the tree rings. One of the effects is lack of snow. When there is not enough snow, then the air surrounding the shrubs is much cooler than below, and the winds are strong, and they somehow cut these shrubs. So shrubs, at least in Yamal, they are growing at the lower parts of slopes in the valleys where they are well covered by snow in winter. So what happened when the mound starts to grow, this gas-inflated mound, which later erupted into this crater. Willows start to rise over the regular surface, and then wind blows out snow from these shrubs, and they start suffering. And the higher is the mound, and the closer the shrubs are to the top of this mound, the more snow is blown out and the more impact is on the tree rings. So this was studied, gave some interesting results concerning the time of start of the mound growth. It was about 1947. One more source of type of information we can get from remote sensing is, of course, dating the crater event. This is crater number 2, for which we have a good sequence of spot 5 images, and we can see that first that upper and lower left image shows some white object, which is mound, and the lower right image shows a black object, which is the hollow. So that's how this crater was dated, and with the accuracy of about 20 days. It was good. For crater number 1, we don't have good high resolution images of to narrow down the dating, so it was done using Landsat images, and it was so what we got from these Landsat images was late October 2013, but now people say they found images from Russian satellite resource, which we don't have access to yet, and this allowed them to move this crater formation to March 2013. So I don't have this data yet, so I'm still thinking it was October 2013. And the other image for this Antipoetar crater, you can probably see that there is a very small mount, not as pronounced as here, very small mount, and much smaller than the crater itself. So there was some other mechanism. But this crater was also much less deep compared to the first one. Maybe this is the reason. The crater is something very big, very small, very local, very deep, and its effect is it still produces methane. But this methane is dissolved in the water, and there is some emission from the lake itself, and all is very, very local and wouldn't affect Sandra, I would say. There are some more effects of the crater is at the distance to which these pieces of frozen deposits and ice were thrown out, and this distance studying remote sensing data appeared to be much larger than we first expected. The farthest piece of block of ice that affected the ground and can be seen was more than almost 300 meters away from the crater. So we subdivided two forms of microrelief, two landforms. Positive, which are these piles of, this is clay and this is sand, such piles of deposits which were first frozen, then of course thawed, and then a little bit washed out. So this is 2016, you can see all the, I would say, traces. This is a fresh one in 2014. But these are positive microforms, and there are also negative microforms, which appeared because of these big, huge blocks of ice managed to kick out the hole in the ground. So this, after this ice melted, it filled this hollow and resulted in such a roundish small ponds filled with mud and water, and some are even 1.5 meters deep. So it was a real good peak. We have to prove that all these lakes were not resulting from, let's say, crater satellites. Small craters around the big one, the family of craters like it happened, for example, for the pock marks in the sea bottom. So we took the earliest helicopter picture and a number of images, and we managed to identify all these the numbers are identified landforms, positive and negative, that were also found on the images after the crater formation and were not found on the images before the crater formation. This is something that very high resolution images allow us determine great. Monitoring of GC1 evolution gives us results that spoil all our first ideas that we will find former craters studying roundish lakes. First, it was widening and filling in with water, snow, and deposits from the sides. So the depth reduced, and the voids grow, and finally, at this already in 2016, we have something like a usual lake with very regular shape and nothing roundish. So what happened with the depth? It starts to fill with water and sediment, and all this starts to freeze from the bottom and from the walls. because the lake is, though it is deep, it is very small in area, so it would not give much warm temperature to stop permafrost. Maybe it is not frozen and full. Maybe they could be still layers of frozen water. We will expect that when everything is frozen, we will probably have a pingo on top of this crater lake. When it's now it is about 4 meters deep, maybe it will be less when it starts to be less than 4 meters. I think it should start freezing also from the top and will freeze in full and form the pingo. That's my hope to still observe. And this is a picture from the end of 2017. One more very interesting thing happened. Though the lake coast is higher in elevation compared to the nearest lake, but it happened so that this is the crater lake, and it eroded somehow path to the nearest small stream, and through this, and then it eroded the piece of the shore which separated the lake and the crater lake. So this, the regular lake drained through the crater lake into the stream, from here to here to the stream. And now we have crater lake, which is 4 meters deep, and we have exposed bottom of normal thermokarst lake, which this summer is very interesting. What we see this summer, after this winter was very close, it should have started freezing and forming pingos under the global climate warming. See permafrost degradation. Lots of work was done with geochemistry because we are interested in what happened to methane, where it comes from, and what is its use and how it will affect the surroundings. So we sampled main objects, which are ice, frozen sediments from the crater walls, water from the inner lake. We did it both in summer and in winter beneath the lake ice, which appeared to be give very interesting results also. And we tested background ice and frozen sediments from the exposures, lake water from normal lakes, lake ice and snow cover. Snow cover because it also falls into the crater and determines its water properties. So this is how it happens, hanging on the rope and keeping this settling the ice, and using both to sample water in the middle of the crater lake, and sampling water from the ice. Both is because it was fall and ice was very thin and it was dangerous to just walk on it. Both is like for security. And this is a regular exposure which existed before any craters and will exist long after, due to slow processes. This is just sampling the lake, where we cannot sample all the lakes from the boat because simply there is no such time. It's during some expeditions, but we can always sample from the coast, and it appeared to be, after several laboratory tests, appeared to be quite representative of the taken from the coast. And this is drilling of the ice and sampling ice and the water beneath the ice. There's only some geochemical results because it will take a couple hours to explain all we have. The salt organic carbon is like more or less a source of methane. This year there were microbiologists who went with us in field, and they also sampled bottom deposits and lake water, and they will tell us hopefully some news about microbiological life and methane sources from the Yamal lakes and crater lake. You can see that organic carbon first sample was very high, and that then it falls down almost to the amount in regular lakes. That's because first organic got into the crater through the surface, all the surface organic layers and vegetation and all that fall back to the water and fall from the coastal erosion. And later, when coastal erosion was already very, very low and little of vegetation also got into the crater, it reduced dramatically. Also, we can see that the soluble salts also reduce in time. And that's because the sediments in the crater walls are mainly of marine origin, and they contain lots of marine salts, which were not washed out because it was clay. So with time, this crater lake water starts to be mixed with the rainwater, with snow water, and thus it's salinity. Of course, our beloved geochemical topic is isotopic composition of water, rain, and mainly ice. We have tabular ground ice, lots of other types of ice sample. We cannot say with ice wedges, those who know, we can say what was the source of water and what was the climate when ice wedges were formed. For tabular ground ice, we cannot say this. There is no such way of interpreting. So we just compare what we have in the crater walls and what we have around. So we can see that tabular ground ice. Right. Is more or less the same as isotopic composition, more or less the same as water from the craters. They are a little bit different from tabular ground ice in other permafrost areas, though in Yamal. But this may be resulting from different types of tabular ice, because it is different. There are two layers. Normally we subdivide two layers. And different properties. So what happened when we measured methane in the crater lake to the left and in the normal lake to the right, but rather deep below? Shallow lakes on Yamal are not very widely distributed. There are lots of quite deep lakes. Because even if they are thermokarst lakes, this thermokarst is resulting from melting of the thick layers of tabular ground ice. So what was the result? You can see that these blue lines are winter measurements under the ice, and yellow are summer measurements. So in winter, methane concentration is much, much higher than in summer, and in winter and in near the surface it is much lower than at some depth, which allows us to somehow to decide that there should be a source of methane somewhere near the bottom. And with this normal lake in winter, the same picture, very high methane at the bottom, lower at the top. But in summer there is no gradient because lakes, different from the small crater lakes, normal lakes have a very high level of mixing by wind, top to the bottom. If we compare this methane concentration in average for GC and for Yamal lakes, you can see that crater have incomparably large amount of methane in the water and in the ice from the walls compared to normal Yamal lakes. Though there are some lakes with a high methane content, concentration, but in average it is very low. We measured isotopes of methane also to understand where this methane comes from. And there is a diagram which shows that most of this methane comes from bacterial origin, not from deeper layers, which somebody expected. That there is some fault in the permafrost through which gas from over 1 kilometer, something like that, deposits which are a production layer of gas deposits somehow managed to penetrate the permafrost into the crater. So this is not the case. So finally, we were going to easily predict, or at least reconstruct conditions of crater formation and estimate the risk. So shall we now? We are somehow under question. Shall we study mounts? Maybe some mounts are going to become craters. We shall study lakes, because maybe lakes are resulting from former craters and still have methane sources. Or do we just do methane survey, like maybe survey of the whole surface of the Yamal, finding like people in the marine conditions are looking for deposits of gas. Yes, they just make geochemical survey of along some transects and find the places where there is extremes. So maybe we should do the same methane survey of Yamal and find these gas extremes. And the second question that we were going to approach, what is and probably would be the risk if more craters appear? With this, we can say that none of the craters we know appear near any settlement. I think it is because when settlements are built, there are lots of boreholes drilled, and production boreholes and just engineering boreholes, and they simply reduce the pressure of any gas that could have been there. And I even have seen myself when drilling several boreholes before construction of the railway, all these boreholes were gassing. So this gas was, so the pressure was somehow reduced. One thing, and the second thing, we still have, I'm sure, 6, okay, let it be 8 craters, very small, and the methane that can that is emitted from these landforms wouldn't add anything to the general methane pools. And so, all questions anyway. So now about this, the hypothesis out of what we have known till now. So initially, first crater was more than 70 meters deep, which is direct measurement, even when some lake was already at the bottom, so maybe even more than 70. And only 18 meters in the diameter at the top, the widest part of it. So the mound, we call it from the beginning, the bulge, was 50 meters in diameter and 5 meters high, which is calculated from digital elevation model. Ice was found to the depth of, from the depth of about 4 meters to the depth of about 25-30 meters. This is direct measurement and geophysics. And below are also icy deposits. Measured during the first visit, methane concentration at the bottom was found much higher and at the crater mouth, little higher than in the background. Tabular ground ice, in our opinion, serves as a cover for possible gas emission immediately to the surface. It promotes its accumulation to produce sufficient pressure to break the upper permafrost cover. Prior to the expulsion, gas accumulation starts to inflate the mound of a specific shape, which grows for several decades. The crater formation can be attributed to the air temperature warming trend and extreme summer events. The warming trend resulted in increased ground temperature, which released enclosed gas bubbles and caused decomposition of gas hydrates within permafrost. At first stages, this caused formation of gas-inflated mound, which is greater predecessor, and later its outburst due to pressurizing over the limits that permafrost can withstand. And thank you for your attention.
Hey, thank you, Marina. That was an excellent overview, and very detailed description of your past 4 years of studies on the craters. So we're up against towards the end of our hour of this month's webinar, but if folks want to stay on, and actually, Marina, are you available to stay on the line for another, say, 10, 15, 20 minutes or so to field some questions?
Yes, sure.
That's okay. Okay, great. Yeah, so I'll open it up right now to questions. If anybody has them, feel free to directly ask Marina. And if you don't have a microphone, feel free to type in the chat box, and either myself or Meredith can relay the question.
Okay, this is Carolyn Rupel. I'm at the USGS, head of the Gas Hydrates Project. So Marina, that was really awesome. It's the most coherent presentation I've seen on this topic. I wanted to ask, obviously, a little bit about the hydrates. There's, as we all know, plenty of methane in permafrost that doesn't have to be bound in hydrates. And for pure methane hydrate to be stable would be hundreds of meters down in these conditions. So you don't detect higher order hydrocarbons, correct? That's what would be required to have shallow hydrates here. Have you looked for higher order hydrocarbons like ethane or propane or anything?
I'm not sure I quite understand.
Have you looked at hydrocarbons besides methane? Because those, okay, go ahead, sorry.
Yes, sure. We have very little from 0 to 000 something at the limits of the method. Very little.
Okay. Okay. Okay, so thank you. That's the reason I asked that question is because only hydrates that include a certain amount of higher order hydrocarbon are stable at shallower depths. And so for pure methane hydrate, the shallowest occurrence should be a few hundred meters, maybe 200 meters or so down. And so I was thinking maybe that a lot of the methane was originating within the thawing permafrost, because we all know there can be a lot of methane in thawing permafrost or produced during microbial processes that act on newly thawed organic carbon. So have you looked at any ages of the methane yet?
No, not yet. Yeah, we are planning when we get more funding for this.
Oh, okay, great.
About methane stability, I never said this. Hydrates were stable. They are not stable. They are, we call them, I'm not studying these gas hydrates. I am using some of this information, but there is lots of study concerning Yamal's gas hydrates from the upper parts of permafrost, because it's not stable, but is in the form of clatrates.
Yes, ma'am, I'm aware of those studies. They're very controversial in our field. So thank you very much. It was a great talk. Thank you so much.
Okay, any other questions over the phone? Because a couple have come in over the chat that I could bring up really quick for Marina. Okay, hi Marina. So this is a question coming from Matt Heebner. So he asked if there's any evidence of ignition or burning of any methane when the crater releases.
This crater number 1, I looked very attentively for any traces of burning and didn't find any. People who were visiting the last crater, which formed in 2017, first it was the observer, the reindeer herder, who said that he saw fire. But he saw it from some distance, and actually I do not very much believe to such evidences because sometimes they want to be interesting. The people who were there, they said there was something black, and they think these black traces are traces of burning. I don't know. Unless I see something myself, I wouldn't believe, because people need to have experienced eyes to understand what they see. There is there can be moss, black moss, which is resulting from decay, not from fire. So I cannot say. Photographs that I have seen, none of them show any traces of burning, but they do not cover everything. So theoretically, it is possible, because with concentration of 10% of methane, it can happen any moment that it what the right word. So it makes a big noise.
Okay, great. Thanks, Marina. Yeah, if you're okay for one more question, here's one from the chat box from Gleb. So he asks, or says, on the slide with the isotopes of water, it looks like a heavier water precipitated in lake waters compared to other Yamal lakes. Is there anything known about groundwater and groundwater exchange on the Yamal with the surface?
Oh, groundwater is sub-permafrost. There is no permafrost. Inside permafrost, there is no water horizons. There are only lenses of what we call cryophytes of saline water. And these lenses are not connected to anything. They are closed. Sub-permafrost water, for Yamal, I don't know any information that there can be open talik, which is non-permafrost from the surface to sub-permafrost. No open taliks, which would have connected sub-permafrost water with surface waters. So I don't believe there is any connection these days when there is continuous permafrost on the mountain.
Okay, great, thank you. Any other, oh, go ahead, Marina, I'm sorry.
No, I'm asking whether I answered the question. Maybe it was something else.
Yes, yeah, no, that's an excellent answer to the question. And so just got a note from Meredith that she has to get off the call in a second and go to another one. And there was some uncertainty whether our call here would drop when she does this. So I'll just ask one more time really quickly if there's any other questions on the phone before everything potentially comes to a halt here.
I don't understand.
You're okay. Yeah, I'm just asking the folks on the phone. So yeah, hang tight, Marina. Okay, great. Well, I'll take that as everybody's kind of satisfied here today. Thank you, Marina. That was an excellent presentation. I think you shed a lot of light on some pretty mysterious features for us over here, just because we don't see these features in Alaska. Do you think there's a possibility that in the future these features might show up in other parts around the Circumarctic, or you think this might be something that's somewhat site-specific to the Yamal and the area around the Yamal Peninsula?
I think it is specific to the area where the top part of permafrost contains gas and gas hydrates. So
Okay, excellent. Excellent.
Same properties then maybe, but I doubt.
There is one more question in the chat from Gleb.
Okay, go ahead. Go ahead, Meredith.
It's on the slide with isotopes of methane. He's referring to the thermogenic methane was sampled from some productive borehole. How was it sampled?
Methane in my results, methane from productive boreholes. No, we don't have boreholes. We are measuring methane in the lake water and ground ice, which is in the walls of the crater and any other exposures. We are working only with the surface. And productive horizons are very deep, and boreholes that reach them are 1 kilometer, 2 kilometers, 3 kilometers deep. So we are not dealing with that gas. And I don't believe that that gas can somehow reach the surface through permafrost, because there are no open talix, there are no faults, tectonic faults that can be open and allow gas to the top. Somebody else is speaking about that, but not me. Was it the answer?
Okay.
Okay, great. Thanks, Meredith, and thank you again, Marina, for staying up late tonight to join our monthly webinar and giving an excellent presentation. So I'll wrap up the call here right now and put a plug out for our June monthly presentation. I believe, correct me if I'm wrong, Meredith, that Paul Schuster from the USGS will be speaking on the release of mercury from thawing permafrost in Alaska. And I don't know if we have a date lined up yet, but I imagine it will be somewhere in the middle of the month of June. And Meredith will be sending around an invitation to everybody on the PCT member list, and then we'll also forward that on to various listservs. So yeah, stay tuned for the details on the June presentation. And thanks again, everybody, for calling in today and participating and joining in our group discussion. And thanks very much, Marina.
Yep. Thank you.
Have a good evening. Goodbye.
Bye.
Thank you, Ben. Thank you, Marina.